The electric field is given by 6I plus 5J plus 3K. The electric flux through a surface of area 30I meters square lying in the YZ plane. Okay, so it is lying like this in the YZ plane. Okay, and this is the field, the area vector. So therefore we have flux is equal to E dot A. This becomes 6I plus 5J plus 3K Newton per coulomb dot, okay, how much? It's 30I meter square. So therefore J dot I is 1, so therefore it's going to be 180 Newton meter square per coulomb, because J dot I is 0 and K dot I is also 0. So therefore the answer is going to be C, and this is the SI unit of flux, that is Newton meter square per coulomb. Thank you. Electrostatic potential due to an electric dipole at a distance r varies as. Okay, so let us see this. So this is the diagram which shows the electric potential due to a dipole. So therefore if you can clearly see, so it varies as 1 by r square. So therefore B is going to be the answer. Thank you. Two identical charged spheres are suspended by strings of equal length. So this is what is happening. Okay, the string makes an angle 37 degree with each other when suspended. So this is 37 degree. When suspended in a liquid of density 0.7 gram per centimeter cube, the angle remains the same. Okay, so let us see here. This time we have suspended it in 7 degree. Okay, we have suspended in a liquid of density 0.7 gram per centimeter cube. Okay, now observing the first part which is in air, and this one which is in liquid. Okay, so now if you see here, the force is mg and here the force is kq square, because there are two identical charged sphere. So if it is having q, this is having q, so therefore kq square divided by, if suppose the distance between them is x, so therefore kq square by x square. Okay, now coming here it's mg, this side, here it's going to be kq square divided by, now the distance is same x square, but there is dielectric, so we are writing the dielectric constant to be d, and there is also an upthrust due to the liquid. Okay, so the upthrust is going to be, that's rho of liquid, which is 0.7 gram per centimeter cube into the volume of the sphere into g. Okay, but again here also what is happening, the angle is remaining the same. So angle is remaining the same. So if you see, this is theta, so this is also theta. Okay, so this is t1, let us, this is t1 and this is t2. Okay, so if you see here, t1 theta, so this is also theta, so t1 cos theta is equal to mg, t1 sin theta is equal to kq square by r square. Now since theta is same, so therefore tan theta, you will find that tension gets cut off. Okay, so in both the cases tan theta is going to be the same, so therefore we'll write tan theta is same in both the cases, so therefore kq square by r square, okay, or x square, okay, kq square by x square into 1 by mg should be equal to kq square by dx square into 1 by, now this is mg minus 0.7 gram per centimeter cube into volume into G. So kq square by x square is gone, this is also gone, and G is also gone. Okay, of course G was not here, it should be outside. Now fine. So therefore we have M. Now what is M? M is 1.4. Okay, so 1 by 1.4 gram per cc into volume should be equal to 1 by d into, now this is again M, so 1.4 minus 0.7 is 0.7 gram per cc into volume. Gone, it's 2, so therefore the dielectric constant becomes 2. So therefore the answer is 2. Thank you. A particle of charge minus q and mass m moves in a circle of radius r around an infinitely, so this is an infinitely long charge of linear density lambda. Okay, and this is from plus infinity to minus infinity. So due to this, the electric field becomes lambda by 2 pi epsilon naught r. Then the time period will be given by, so therefore if we have mass m is there and this is the electric field in this direction, the charge is minus q, so therefore it's going to experience force as q into E. So therefore we have q into E is equal to m v square divided by r. So therefore v becomes r q E divided by m root. So this is first thing. Now time period is going to be 2 pi r divided by v, because 2 pi r is one revolution, and the velocity is v. So therefore in one revolution what is going to be the time taken, that's the time period. So therefore it's going to be 2 pi r divided by v, which is root over r QE into root over m. Okay, now we do everything here. 2 pi r divided by root over m by rq into E. E is lambda by 2 pi epsilon naught r, so lambda by 2 pi epsilon naught into r. Okay, so fine, so r and r is gone. Okay, and this 2 pi epsilon naught is so k is 1 by 4 pi epsilon naught, so therefore we can write 2 pi r divided by root over m into 2 we do, so this becomes 4 pi epsilon naught divided by 2 divided by q into lambda, which becomes 2 pi r into root over m by 2q lambda into k. Okay, so 2 pi r into root over m by 2q lambda into k, so therefore B is going to be the answer. Thank you. Two charges q and 3q are separated by a distance r in air. This is q and this is 3q, and they are separated by a distance of r in the air. At a distance x from charge q, the resultant electric field is 0. The value of x is, okay, so the value of x, so this should be x, because the electric field, if you see, from q it's going to be like this, from 3q it's going to be like this. So if this is x, this has to be r minus x, so therefore electric field we can write here k q divided by x square should be equal to k into 3q divided by r minus x whole square. kq is gone, so therefore 1 by x is equal to root 3 divided by r minus x. R minus x is equal to root 3 x, so therefore x becomes r divided by 1 plus root 3. So therefore C is going to be the answer. And we can see here that due to q it's going to be in this direction, due to plus 3q it's going to be in this direction. So it has to be in between q and 3q only, because if it is here, if you see here, both the electric fields are pointing in this direction, they can never amount to 0. Same thing here also. So therefore this x is has to be in between q and plus 3q, and therefore it's r divided by 1 plus root 2. Thank you very much. In the charges, plus q and minus q is 2l, okay, and minus plus 2q and minus 2q is 4l. The electrostatic potential at point P at a distance r from the center O is this much, where the value of alpha is. ठीक है, तो अब देखिए ध्यान से, पहले सबसे पहले पोटेंशियल का हम लोग फॉर्मूला देखते हैं. ये डायग्राम अच्छे से आप नोट डाउन कर लीजिए, क्योंकि दिस डायग्राम इज लाइक है ना, इलेक्ट्रिक फील्ड ड्यू टू अ डायपोल एंड इलेक्ट्रिक पोटेंशियल ड्यू टू डायपोल का ये समरी है. तो पोटेंशियल देखिए ध्यान से क्या है, के पी कॉस थीटा डिवाइडेड बाय आर स्क्वायर. P is the electric dipole moment, which is Q into D. K is 1 by 4 pi epsilon naught. And theta is important here. If you see, theta is the angle from the positive Q charge. Okay. And R is the distance from the center of the dipole. Okay. So now let us go ahead. Okay. So here if you see, there are two dipoles, minus q and plus q is one dipole, and plus 2q and minus 2q is the another dipole. So therefore now we have to find out the electrostatic potential. So for the minus q and plus q dipole, okay, the potential is going to be kp cos theta by r square. So k into P, which is Q into 2L, into cos theta, which is cos 60 degree, okay, divided by R square. For the plus 2Q and minus 2Q dipole, it's going to be, potential is going to be K into 2Q into 4L, which is the dipole moment, into cos of, this is 120 degree, because the theta is taken from the positive. Now here also we can see that the theta is being taken from the positive charge. Okay, so it's like this, divided by, this is also r square. Okay, now the potential is a scalar quantity and it's going to be algebraically added. So therefore V total is equal to V1 plus V2, which is equal to K Q L by R square into 2 into cos 60, it's 2 into 1 by 2, plus it's 8 into cos of 120 degree, which is cos 120 degrees minus half. So this is minus half. So this is 4, this is 1. Okay, so minus 4 plus 1 is minus 3. So minus 3 KQL divided by R square. Now we should take K as 9 into 10 to the power 9. So minus 27 into 10 to the power 9 Q into L divided by R square. So if you see, QL by R square is there, 10 to the power 9 is also there, so therefore alpha should be 27. So therefore the value of alpha is 27. Thank you. Force between 2 point charges Q1 and Q2 placed in vacuum. So this is Q1 and this is Q2, and these are placed in vacuum at r centimeter apart, is F. So therefore F is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R square. This is first thing. Force between them when placed in a medium having dielectric constant, so Q1, and now it is R by 5. So this is R by 5 and it is placed in a dielectric constant K is equal to 5. So therefore this force F nu is going to be 1 by 4 pi epsilon naught into 1 by 5, because dielectric constant should also be multiplied, into q1 q2 divided by r by 5 whole square. So this becomes q1 q2 divided by 4 pi epsilon naught into r square into 1 by, this is 1 by 25, so this becomes here 25, this is 5, so this is actually 5f. Therefore B is the answer. Thank you. Spheres are suspended by strings of equal length. Okay, so this is string and this is also a string, both are of equal length. The strings make an angle of theta with each other. When suspended in water, the angle remains the same if the density of the material of the sphere, when suspended in water, so now this is in water, okay, and the angle is going to remain the same. So the density of the material of the sphere is 1.5 gram per cubic centimeter. The dielectric constant of the water will be, so here this is going to be mg, okay, and it's a sphere, okay, so therefore mg rho, which is 1.5 gram per cubic centimeter into 4 by 3 pi r cube, so 4 by 3 pi r cube into g, and this was tension T. Now this is theta, so this is going to be theta by 2, and this is the force, so the force is going to be K into Q square divided by, if this is x, so x square. Now this is suspended in in water, so and still it remains at theta only, okay, so this is T1, this is T2, here it's again 1.5 gram per cc into 4 by 3 pi r cube g, but there is above a thrust also, which is of 1 gram per cc into 4 by 3 pi r cube into g. Now this force is having a dielectric constant also, so let us say, so this is k q square by x square, and this is 1 by d. Now here also the theta is going to remain the same, so it's theta by 2. So therefore we can clearly see that for the angle you can see theta by 2, so this is also theta by 2, and this is also theta by 2. So therefore in both cases tan theta by 2 remains the same, so therefore so tan theta by 2 in this case is 1.5 gram. How it's tan theta by 2? So like I'll show you. So 1 by cc into 4 by 3 pi r cube divided by kq square by x square should be equal to should be equal to 0.5 gram per cc into 4 by 3 pi r cube, both sides is multiplied by g, divided by kq square by d x square. Gone, these all things are gone, and this is just 3, so therefore d becomes 3. So now what we have done here is we have taken the ratio, okay, of course this is cot theta by 2. So in both the cases, because theta by 2 is remaining the same, so therefore the force in this direction and force in this direction is going to be same, not same, but the direction, the theta is the same, so therefore cot theta by 2 is this entire thing is cot theta by 2, and this is also cot theta by 2 only because the angle is again the same, okay, so therefore the dielectric constant is going to be 3. Thank you. So the two hollow concentric cubes enclosing charges 2q and 3q respectively as shown in the figure. The ratio of electric flux passing through C1 and C2 is. So this is C1 and this is C2. Okay. Now we have to find the electric flux which is passing through C2. So that electric flux is going to be Q enclosed divided by epsilon naught. Q enclosed divided by epsilon naught. So what is the charge which is enclosed inside C1? It's 2Q. So therefore it's going to be 2Q divided by epsilon naught. Whereas the electric flux passing through C2 is going to be equal to the total charge enclosed inside C2. Okay, so C2 is having the charge, this charge also, which is 3Q, and this charge also, which is 2Q. So therefore how many charges? Total charge is 5Q. So therefore 5Q by epsilon naught is the electric flux which is passing through C2. So therefore the ratio is going to be 2Q by epsilon naught divided by 5Q by epsilon naught, which is equal to 2 by 5. So therefore A is the answer. Thank you. Suppose a uniformly charged wall provides a uniform electric field 2 into 10 to the power 4 Newton per Coulomb normally. So this is the wall. And this is the electric field, which is 2 into 10 to the power 4 Newton per Coulomb. A charged particle of mass 2 gram is suspended through a silk thread of length 20 centimeter and stayed at a distance of 10 centimeter from the wall. So this is the silk thread and it's like this. Okay, so this is the ball. Okay, and what is it? The distance is 10 centimeter. Then the charge on the particle will be this. So basically now this is mg, this is t, and this is this force due to the electrostatic field. So this is going to be q into e. Now this is 20 centimeter. So therefore we can see that this theta is going to be, so cos theta is 10 divided by 20, which is 1 by 2. So therefore this is going to be 60 degree and this is going to be 30 degree. So therefore if you see the free body diagram, it's it states that T cos 60 degree is going to be equal to QE. T sin 60 degree is going to be equal to mg. So therefore tan 60 degree, which is root 3, is equal to mg divided by QE. So therefore Q becomes mg divided by root 3 into E, which is, the charge particle's mass is 2 gram, 2 into 10 to the power minus 3 kg into G, which is 10 ms minus 2 divided by root 3 E. E is 2 into 10 to the power 4 Newton per Coulomb. Okay. And this was again with kg. So kg ms minus 2 and this is gone. So Coulomb goes up. 2 and 2 is gone. So therefore this becomes okay. So this is gone. This is 3. So this is 1 by root 3 mu coulombs. So therefore x becomes x. So 1 by root x. So therefore x becomes 3. 3 is the answer. Thank you. Two charges of plus 5q and minus 5q are situated at the points 3a, 0 and minus 5a, 0. Okay, so let us take this to be the x-axis. This is the y-axis. So this is plus 3a, 0 and this is minus 5a comma 0. This is 5q and this is minus 2q. The electric flux through a sphere of radius 4a having center at the origin. Okay, the radius is 4a, so therefore it's going to be something like this. So this is 4a radius. So therefore the electric flux is going to be equal to q enclosed divided by epsilon naught. Now what is q enclosed? Only this charge is getting enclosed. You see, this is outside charge. So therefore it's going to be 5q divided by epsilon naught. So therefore B option is going to be correct. Thank you. Math list 1 with list 2. ठीक है, एक एक करके देखते हैं. So this is the first one. So if you see, this is Ampere's Maxwell law. So what Ampere's Maxwell law states? It states that the magnetic field over a closed loop is equal to mu naught I plus mu naught epsilon naught d phi E by dt. This I is conduction current, which is here, and this entire thing is displacement current, which is id, which is here. So therefore the first one is Ampere Maxwell law. The details of it, like, it will take good amount of time to understand, but yes, just in a nutshell. So if you see, this is the wire and this is a capacitor. So now we all know that the capacitor, there is no current flowing inside the capacitor due to conduction current, because the charges actually get accumulated here. Okay, so now what happens is that this wire is having a magnetic field around it. Okay, magnetic field around mu naught I by 2r. Okay, this has a magnetic field around it. Okay, fine. Now mu naught I by 2 pi r. Now what happens is that this magnetic field is going to be continuous. So here also some magnetic field is there, but here there is no current. So how we define current here? So here current is known as displacement current, and the value of it is epsilon naught d phi E by dt. Okay, so therefore this is going to be the entire formula of this. Okay, so this is the Ampere Maxwell law. Now going ahead, we have this is the second one. This is the Faraday's law, which is EMF is equal to minus d phi by dt. Now what is EMF? EMF is the potential difference. So potential difference is basically dV is equal to minus E dot dr. This is mentioned here. This is actually EMF only. Okay, E is electric field. So this is the formal version of the Faraday's law, which we can see here. This E dot dl, this is going to be giving us dV, which is the EMF, this is equal to minus d phi. Now what is phi? Phi is the magnetic flux, which is B dot A, and A is this is the unit vector in the A direction. Okay, so therefore this matches for Faraday's law. Okay, now going ahead, there is E dot d equals q, and this is our very dear Gauss law. Okay, where the electric flux is equal to the charge enclosed inside the Gaussian surface divided by epsilon naught. And then there is the Gauss's law for magnetism, which is B dot dA is equal to 0. So what it states is that the net magnetic flux of the magnetic field must always be 0 over any closed surface, because the magnetic field lines actually, they don't originate, they are always in a closed loop. So therefore the magnetic flux, the net magnetic flux must always be 0 over any closed surface. Okay, so you see here the magnetic field lines are entering, here they are leaving. In case of electric field lines, there is a charge enclosed, so therefore you will find all the electric field lines, they are leaving from the surface only. From the surface they are just leaving. but because magnetic field lines are always in loops, so therefore they will enter and then they will leave. Okay, so therefore this is a very dear Gauss's law for magnetism. This was Ampere Maxwell law. This is Gauss's law for electricity, and this becomes the Gauss's law for magnetism. So therefore we have A4. Okay, then B is okay, B we have not done, so B is 3, the Faraday law. C as 1, Gauss's law for electricity, and D is Gauss's law for magnetism. Oh, no, not this. This is Faraday law. Okay, so A4, B3, C1, D2. Okay, thank you. Electron is moving under the influence of the electric field of a uniformly charged infinite plane sheet. So if this is in the infinite plane sheet, so this will be producing electric field of sigma by 2 epsilon naught. It's a uniformly charged infinite plane sheet S, and this is having a surface charge density as sigma. So now here at 1 meters, okay, at 1 meter distance, there is an electron which is having a speed of 1 meter per second. Now the speed here, that what it is mean, the speed can be in any direction. In any direction the speed can be there. Okay, so now the maximum value of sigma if the electron strikes. Okay, so if you see, now the electron is going to experience a force in this direction, which is E into sigma divided by 2 epsilon naught. Basically E into electric field. This is the force which is experienced. So therefore the acceleration becomes this divided by mass of the electron. Now what should be the maximum value of sigma? So if you see, if the speed is in this direction, okay, so it will require minimum acceleration to strike here in 1 second. If the speed is, suppose in this direction, it will require some more, but if the speed is in this direction, then to strike it you require the maximum acceleration. Okay, so therefore the speed, the direction of the speed or the direction of the velocity must be in this direction. Okay, so therefore you see what we can write is ut minus half at square should be equal to -1. So u is 1 meter per second into 1 minus half into a into t, again it's 1, should be equal to -1. So half a should be equal to 2. So a becomes 4 meter per second square. This is the maximum value of acceleration. Now this 4 should be equal to E into sigma divided by 2 epsilon naught into 1 by me. So therefore sigma is going to be 8 epsilon naught mass of electron divided by E. So therefore the value of alpha is going to be 8. Thank you. Given below are two statements. One is labeled as assertion and the other is labeled as reason. Assertion: work done by electric field on a moving positive charge on an equipotential surface is always 0. Yes. Why? Because moving a positive charge on an equipotential surface. So if this is the equipotential surface, okay, so we have dV is equal to minus E dot dr. Sorry, dV is a scalar quantity. Now dV is going to be 0. So this, if this is the dr, then electric field is going to be in this direction. Okay, so therefore because it's going to be 0, so dr and electric field both are non-zero, so therefore the dot product should be 0, so therefore it should be cos 90 degrees. So therefore the angle between E and dr should be 90 degree. So for an equipotential surface, therefore the electric fields lines are always perpendicular. Okay, either it may be outward or inward. Okay, so yes, it's true, this is true. Now electric lines of force is always perpendicular to equipotential surfaces in the light. Yes, that is also true, this is also true. So therefore yes, both A and R are correct. Okay, now work done by electric field, if you see work done by electric field is what, QE force into dr. Now here again it's E dot dr, so it's again is going to be 0 only. Okay, because the force is in this direction and we are moving in this direction, so therefore the net work done is what, F dot dr. So F is this, dr is anyway this, so angle is 90 degrees, so therefore it's, so both statements are going to be true. Thank you. Two charges of -4 microcoulomb and +4 microcoulomb are placed at the points A and B as shown here. Okay, so first of all let us find out the so this is dipole, because it's already mentioned that magnitude of torque acting on the dipole, so therefore we are finding out the dipole moment P, which is basically Q into D. So Q is 4 microcoulomb into D, which is root over 2 minus 1 whole square plus 0 minus 1 whole square plus 5 minus 4 1 square. So basically this is root over 3 into 4 mu coulomb meters. Okay, 4 root 3. Now it is located in an electric field. Okay, and what is the direction? So direction is from minus Q to plus Q. Okay, so this is minus Q is situated here, plus Q is situated here, so therefore the direction should be I cap. So basically what we are writing is AB vector we want, basically we want AB unit vector, the direction of the electric dipole moment. So AB unit vector is B vector minus A vector divided by magnitude of B vector minus A vector, we get unit vector. So therefore AB unit vector is I cap 2 minus 1 minus j cap plus k cap, and it should be divided by root 3. So therefore we have dipole as 4 mu coulomb meter into root 3 into I cap minus j cap plus k cap divided by root 3. Root 3 is gone. So therefore this is the dipole moment. Now we want to find magnitude of the torque acting on it. So therefore torque is P cross E. So therefore it's going to be 4 I cap minus j cap plus k cap mu coulomb meter. This is cross what? E, 0.2 volt per centimeter, and this is I cap. So now I cap cross I cap is going to be 0. Okay, so this is 0.8. Now j cap cross I cap is minus k cap, so this is going to be plus k cap, and k cap cross I cap is j cap, so therefore it's going to be plus j cap mu coulomb. Okay, and this was volt per centimeter, so this is going to be into 100 now, and this is volts. Okay, so the magnitude of the torque is going to be, so now this is P cross E. Okay, so now everything is in okay, so basically we have removed here, this is coulomb meter, no? And this is centimeter, so therefore we have like put here 100 centimeter, and that's why both of them cancel, it's going to be 100. So mu coulomb into volt, so therefore it is 0.8 into 100, so this is going to be 8 80 into 10 to the power minus 6 j cap plus k cap, and this is Newton meter. Okay, so now this j plus k is, so we have to find the magnitude, so it's going to be 80 root 2 into 10 to the power minus 6 Newton meter. So this becomes 8 root 2 into 10 to the power minus 5 Newton meter. So here clearly alpha is 2, so 2 is the answer. Thank you. The electric potential at the surface of an atomic nucleus Z is 50. Okay, so therefore that means what? 50 protons are inside the nucleus. Okay, how many? 50 protons are there. I'm writing here 50 protons. Okay, of radius 9 into 10 power minus 13 centimeter. So this is the radius. Okay, so therefore it's going to be potential is going to be kq divided by r, which is equal to 9 into 10 to the power 9 Newton meter square divided by Coulomb square into q, because there's 50, so 50 into 1.6 into 10 to the power minus 19 Coulomb divided by r, which is 9 into 10 to the power minus 13 centimeter. So 10 to the power minus 13 centimeter, and we are writing in meters, so therefore 10 to the power minus 2 meters. Gone, 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 gone. 10 to the power minus 13 is 10 to the power minus 15. This is 10 to the power minus 4. This is 10 to the power 5. So this is now 9, and 9 is also gone. So therefore 50 into 1.6 is this is 800. 800 into 10 to the power, no, not 800, it's 80. 50 into 1.6, 80. 80 into 10 to the power 5. So this is going to be 8 into 10 to the power 6 volts. It's quite huge. Therefore the answer is going to be 8. Thank you. An electric charge 10 to the power minus 6 mu coulomb is placed at origin. Okay, so this is the origin, and here the charge q is placed, which is actually 10 to the power minus 6 mu coulombs of x-ray. The points p and q are situated at, okay, so this is p point, which is root 3 comma root 3, and this is root 6 comma 0, which is the q point. The potential differences between the points p and q. So here the potential is again kq by r1, and here it's going to be kq by r2, where r1 and r2 are the distance from the origin. Okay, now if we take r1, r1 is going to be root over a square plus b square, so therefore 3 plus 3, which is root 6 meters. Interestingly, both of them are situated at root 6 meters, so therefore the potential is going to be the same. If it is v here, it's going to be v here also. So therefore the potential difference, because both are having the same potentials, therefore the potential difference is 0. Therefore C is going to be the answer. Thank you. A thin metallic wire having cross sectional area 10 to the power minus 4 meters square. So cross sectional area is A is 10 to the power minus 4 meter square, is used to make a ring of radius 30 centimeter. So the radius of the ring is 30 centimeter. A positive charge of 2 pi coulomb. Okay, so this total charge, which is uniformly distributed, is this q is actually 2 pi coulomb, is uniformly distributed over the ring. Well, another positive charge of plus 30 picocoulomb. So here the charge which is mentioned, written placed here is 30 picocoulomb, center of the ring. The tension in the ring is, okay. So now what we do is we take a small part of the ring. Okay, and let us take this as, you know, 2 theta. We're taking 2 theta. Later on we'll understand why we're taking 2. We take it as 2 theta. Okay, so now here if you see, this is how much? This is r into 2 theta. So it will be having some charge also. Now what is the charge in r2 theta? So therefore it's going to be r2 theta into charge per unit length. So this is 2 pi coulomb divided by 2 pi r. Gone, and this is also gone. So therefore 2 theta coulomb is the charge here. Okay, now we are taking theta to be very small. So when theta is very small, so theta can be assumed, so the entire charge can be assumed to be at the center, because it's actually very small. Okay, so so therefore the force between the two charges is going to be, okay, so here it's this is 2 theta coulomb, and here it's 30 pico coulomb. So therefore the force is going to be K into 2 theta into 30 pico coulomb divided by r square. This is going to be the charge. So this is also in coulomb, and this is pico coulomb. Okay, now the question is, what is the tension in the ring? So for that we see this diagram. So you see here we are having 2 theta here. Okay, now we take again a small portion of the ring, and we see, this tension is going to be tangential here. So it's going to be tangential, so therefore the t cos theta is here, t cos theta is here, both t cos theta, they get cancelled out. So therefore net force in this direction is actually 2t sine theta. So this 2t sine theta, okay, this 2t sine theta, should be equal to the force of repulsion here, because you see both are positive charges. This is also positive, this is also positive, so it's going to be in this direction. Okay, so the tension force, the 2t, this is going to counteract here. Okay, so basically the force of repulsion was in this direction, so both of them are going to be equal. So therefore 2t sine theta is going to be equal to how much? K into 2 theta into 2 theta coulomb into 30 pico coulomb divided by r square, and r is 30 centimeter. So therefore 0.3 meter whole square. Okay, so now since theta is very small, so therefore we can write sine theta to be equal to theta, because theta is very small. So 2t into theta should be equal to K, which is 9 into 10 to the power 9 Newton meter square per coulomb square, into 2 theta coulomb into 30. Now this is 30 pico coulomb. Pico is 10 to the power minus 12 coulombs divided by 0.3 meters whole square. So this is 3 into 10 power minus 1, so 9 into 10 to the power minus 2 meter square. Meter square and meter square is gone. Coulomb square and coulomb is gone. So therefore 2 theta and here also is gone. So therefore t becomes, if you see, okay, 9 and 9 is also gone here, and okay, so it is 30 into 10 to the power minus 12 plus 2 plus 9. So tension actually becomes 3 newtons. So therefore the tension in the ring is 3 newton.